So, now we look at, as I hope I motivated you to look at graph problems. Let us take a simple problem. Okay. What I want to do is, let us say you are you want to reach the railway station on time. Okay. Now, you are, let us say, starting from your college and you need to reach the railway station, and let us say this is your college over here, and there are number of different paths that you can take to the railway station. Okay. So, now one would be a direct path which costs you so much. There is another path via some other place which costs you a little less, and so on and so forth. Being a student, let us say this is cost of money taking these various paths. For example, if I took an auto, this would be maybe the cost of the path, but whereas if I took a bus from point A to point B and from point B to point C, this would be the cost. Okay. So, let us say our goal is, being a student, you want to find out what is the shortest path in terms of cost. You have enough ample time and you want to find the shortest path to reach from node A to any of these other vertices that are there in the graph. So, this is called the single source shortest paths problem. Okay. To formally define this, we say we are given a directed graph G which consists of vertices and edges, in which each arc has a non-negative label. Why do we have a non-negative label? Because obviously the cost, there is going to be some positive cost in moving from one place to another. It is not going to be, you are going to pay some, the conductor is not going to give you money for travelling by his bus, although maybe Chennai Transport should do it, but nevertheless that is not what they will do. You have to pay a ticket, and the ticket is going to cost you some positive money. Okay. So, you have non-negative edges on the and there is one vertex which is the source. Here we are assuming that A is your source. Okay. Then what we want to find is, we want to find from the source node A to every other vertex B, we want to find the shortest path, and the length of the path is simply defined by the sum of the costs of the arcs on the path. Okay. So, how do we go about solving this problem? It is interesting that this algorithm uses a paradigm called the it is called a greedy paradigm. We will see what this greedy paradigm is all about in a minute. Greedy means we make solutions which are local. We do not worry about the future at all, we just make a decision right now, and interestingly whatever we see at that point in time, and that is also globally optimal. So, here what I am going to assume is, I am given a graph here. Here C corresponds to the adjacency matrix representation of the graph, and I, without loss of generality, I am assuming that the starting node is 1, which is in this particular case the node A, and I am creating an array di over here, and let us say there are n vertices in the graph. I am just filling up this array with C of 1 comma I. Since there are no self loops, C of the distance to your self node is 0. Okay. Then what I do is, then how do I build this algorithm? The algorithm goes like this. So, what is it doing initially? Here notice that this is my node A. It initially fills the matrix, the vector B, vector D, this is called a vector D in the algorithm over there. It says to the node B, you have, if I look at the directly connected edges, I have a distance of 6. To the node C, I have a cost of 10. To node D, there is no direct path, therefore, I set it to infinity, and to node E, there is a directed path, and I define that cost as 8. Okay. Then what we do is, we simply, if you go back to the algorithm, the idea is that we first include, what is it that we are trying to find? We are trying to find the shortest path to every node. So, first what we do is, we include the node which is closest to the given node into your source vertex list. So, what we do is, there is something called a source vertex list which consists of the node A in this example. Okay. Then what I do is, I form this array. Once this array has been formed, we choose a vertex W in V minus S such that D of W is a minimum. So, what is the meaning of this now? I am choosing a vertex in D such that the distance between the source vertex to any one of these vertices is the smallest. So, what do we find? We find that B is the smallest. So, what do? I include this vertex to S. That means, S becomes A comma B now. Okay. So, what do we have now? We have A comma B, and what do? I compute the distance. Then what we do is for each vertex which is there in V, next look at this one more loop over here. For each vertex V in V minus S, I update the distances. Okay. So, now what do we see now to all the other vertices? That means, now I have the shortest path from A to B, which is 6. Now, what I do is I check whether there is a shorter path to C from A via B. Okay. What did I have? The direct path said the length is 10, but if I go via B, then I have A to B, which is the cost 6 plus 2 8, therefore, this is shorter. So, I update this to 8. So, for E there is no path, so I leave it as it is. Now, we still do not have a path for D, D is still infinite, so we leave it as it is. Okay. The next, what do we do now? Once these paths, so what have I done? I have included the vertex B into the source vertex list. Next, what did I do? I updated the distances to all the vertices C, D and D, the other vertices, to see if there is a path via B, which is what we have done now. All right. Next, what we do is we next include, now what do we have amongst these vertices, we check. So, B is now out of this list. So, I look at I create a new distance matrix which says what is the shortest path to the nodes which are not included in the list. So, what do I have now? I have a path to C which is 8, and I also have a path to D which is infinite, and a path to E which is 8. Okay. So, now I choose either this or this, does not matter. So, let us say I choose 8 C. Okay. So, now what do? I again include into this vertex list A comma B comma C. Now, I check whether there is a shorter path from C to D and C to E, because I am going through C. So, what do I do now? I already know the distance from A to C, which is 8, and then I find there is a path from C to D. So, I had originally the distance as infinite. So, I update this path, and this will make it 6 plus 2 8 plus 3 11. All right. Then next, what do? There is also then once I have completed this, there is no path from C to E, so I leave it as it is. So, now C has been already included, okay, in my source vertex list. So, what do I have? I only have 2 vertices left. Then now I choose E, because E has the shorter distance. So, my source vertex list now becomes A comma B comma C comma E. Then now I check whether there is a shorter path from E to D better than what is there. So, already we know that the distance from A to E is 8. So, 8 plus 2 10, and therefore, I update this list. So, E is already there, and this becomes 10. Okay. Now, I include, this is the only vertex that is left. So, I include it into the source vertex list. So, what do we have now? We finally have the shortest paths from all the nodes to from source vertex A to all the nodes. So, it tells me the shortest path from A to B is 6. Okay. So, what do we have finally? We have B, which is 6, we have C, which is 8, we have E, which is 8, and D, which is 10. So, this is what the shortest path problem is all about. Okay. And this works only when the graph has edges which are non-negative weights. There cannot be any negative weights in the edges of the graph, okay, because if there is a negative weight, I can get into some other kind of problems. For example, let us say that now if suppose this path was minus 10 or something like this, then I already included this vertex in my source vertex list, and you can say that actually the path from A to B, if I go via this, is 0. So, that is not allowed. Therefore, you only have to have positive weights in the graph. This is called the single source shortest path problem, and basically it is very useful for finding distances between a source node and a destination node. To give you an idea, when you look at when you are connecting to the internet to some server somewhere, a kind of in networks, for example, what you do is your data that is being transmitted either from you to a server or from a server to you uses what are called is converted to packets, and the packets actually try to find some kind of a shortest path to transfer the data from one node to another. So, it is continuously computing these shortest paths. Okay. So, this completes the Dijkstra's algorithm. The next algorithm that I want to talk about is another problem which is somewhat of a related problem. And this again comes from communication networks. The idea is the following: you want to find what is called a minimum cost spanning tree. Let me tell you why this. Let me motivate this problem. Here is a graph which you can see on the left hand side. There is a graph that is given, and on the right hand side it gives you what is called a minimum cost spanning tree. That means what we want to do is, the idea is to reach all the nodes in the graph with as minimum a cost as possible. Okay? That is the goal in this problem. So, what we essentially do is we take this particular graph which we have, which is connected multiply, as you can see, and then we get this minimum cost spanning tree. So, how do we get this minimum cost spanning tree, and what is the purpose of this minimum cost spanning tree? Let us say now you want to disseminate information across the internet, and you want to do it as fast as possible. Okay? Then a minimum cost spanning tree is what is computed. They are called core based trees, and normally if you give it to any one of these nodes, it will quickly disseminate. It will also ensure that this information is disseminated to all the nodes. Then the nice thing about this is that it finds a tree which connects all the nodes in the graph. This need not, do not confuse this with the earlier problem on the Dijkstra's that we did on the single source shortest path problem, because there it is possible that sometimes when you look at a directed graph like that, there may be no path between a pair of nodes. So, it cannot even transmit the information. Okay. Here on the other hand, the idea is to find this minimum cost spanning tree. So, let me define this problem again. Given a graph v comma e, it is a connected graph, and each edge u v in e has a cost of c u comma v attached to it. So, it is a labeled graph. The job is to compute this minimum cost spanning tree for G. And what is a spanning tree? A spanning tree for G is a free tree that connects all the vertices in B. Okay? So, this is what a spanning tree is all about. You can have anything can form a spanning tree, for example, but we are looking at that spanning tree. For example, I can have 1, 2, 3, 5, 6, 4. This is also a spanning tree. Okay? But there are a number of different spanning trees that are possible. But what we are interested is in that spanning tree whose total weight is minimum. That is, when I add the edges costs, for example, it should be the smallest possible amongst all the minimum spanning trees, or all the possible trees that are there. So, let us see how we can compute this. There are two types of algorithms. One is called the Prim's algorithm, and the other algorithm is called a Kruskal's algorithm. I am going to discuss Prim's algorithm, which essentially builds the tree starting so it does not matter when you are using this algorithm. For example, the idea is that there is nothing like a single designated node as source. Any node can be a source. So, what we do is without loss of generality, again I have started off with one node u as the source, and then what do? We look at the lowest cost edge that is there in the graph. So, let us take this particular example. Let us say 1 is the source node. I take the lowest cost edge from 1 to 3, and this is 1. Okay. So, then what do? I include this edge into the graph or into the tree. So, what is going to give me a spanning tree, right? So, what is happening here now? It is taking the lowest cost edge such that u is in a set called u and v is in a set called v minus u. Initially, the set u consists of only one vertex, which is some vertex which I am starting with. Okay. Then what do? We create a tree with T union u comma v. Okay. Then what are we doing now? Then after we have done this, then what we do? We say u is equal to u union v. That means now I have included the lowest cost edge in the graph, once we have included the lowest cost edge in the graph, then we also find that something called a source list over here also includes the vertex 3. Okay. Next what I do is I have basically vertex 1 and 3 into the source vertex list. Then you have here, if you go back to the graph, there are edges from 1 to 2, 1 to 4 and also from 3 to 2 and 3 to 4 and so on. So, what you do is you look at all these edges, find out which is the lowest cost edge which connects vertices which are there in the U list, source vertex list 1 and 3 and the rest. Okay. Which is the one which is the smallest now? When you look at 1 and 3, if you put them together and look at all the edges that are connecting to the rest of the nodes, clearly 4 is the smallest. So, you take the smallest cost edge, then you include vertex 6 into the list. So, now what do you have? You have 3 vertices in the list. Now, again you find out which are the smallest cost vertices. Okay. Then what do you have? You have 2 as the smallest cost vertex. So, you connect, you include 4 into the source vertex list. So, you had 1, you had 3, you had 6 and then you connected 4. Okay. Then what happens? Then you look at the remaining costs of vertices which are what are there. What do we have now? We only have 2 vertices 2 and 5 which need to be connected, and what do you have? You have cost of 5 and the other edge cost is 6. So, you choose 5, include 2, then after you have included 2, then you find out from 2 for example, again there is only one path over here to connect and you connect to the last vertex. So, this corresponds to the minimum spanning tree. This is called Prim's algorithm. So, you start off with an empty tree. Let me recap this algorithm for you. You start with a source vertex, does not matter, without loss of generality. You have taken 1 to be the starting vertex, and then what are we saying? Until all the vertices in the graph are included in the source vertex list, you keep on choosing the lowest cost edge such that one vertex is in the U list and the other vertex is in the V minus U list, and then you include that edge into the tree. Keep repeating this process, okay, and that gives you the minimum cost spanning tree. Okay. So, this comes to the end of 2 different problems we looked at. One is the single source shortest path problem and the other is the minimum cost spanning tree problem. Next we will look at another set of problems which are based on traversals of graphs. Okay, we will look at unweighted graphs and we will see these two more algorithms on graphs in a short while.